We've previously used the substitution of negative x into the power series, the basic power series, to get this expression. So that notice that negative I've taken out as -1 to the power n. So that negative actually is going to make this series alternate. And then I just get this alternating power series. And that 1 over 1 minus negative x is the same as the function 1 over 1 plus x. Now, it happens that the derivative of log x, when I differentiate log x this way, I end up with 1 over 1 plus x. That means then, if I integrate this function 1 over 1 plus x, I'm going to end up with the function. I'm going to end up with the function. Integrating is going to give me the log function of 1 plus x. Okay. Now, if I can differentiate a function, I can also differentiate a series expression. So that is true. If I can differentiate a function to generate another function, I can generate this series expression to generate another series, and that series will be the same as ln of 1 plus x. So when I put the integral form of this, so notice I'm integrating that yellow highlighted part there. When I integrate that, that should give me a series for log 1 plus x. And by integrating that, I'm going to use the power rule. The -1 to the power n stays the same. The power rule becomes n plus 1, and I need to divide by n plus 1. And that series, when I expand it out, this series then represents my expansion to calculate log of 1 plus x. What this means then is I have this irrational number, like for log of some number is usually irrational, and I could calculate that irrational number by plugging into some polynomial function, which is just add, subtract, times, and divide. So this can be done as a calculation, whereas before I needed a calculator, some calculating device or something that had log stored in it to be able to do a log value of some number. Okay, so we're going to do an example of this. So here the previous example I integrated, but we can also differentiate. So I'm going to start with the same function. I'm going to plug in the negative x to get the 1 over 1 plus x. That function is this one here that we've already identified, that highlighted in yellow. So what we're going to do is we're going to differentiate that 1 over 1 plus x. That means we can differentiate the series that represents the function 1 over 1 plus x. And so I'm going to differentiate -1 to the n, x to the n. And when I do that, my series I generate will be equivalent to 1 over 1 plus x all squared. So differentiating this from n equals 0 to infinity, the -1 doesn't differentiate. I'm going to end up with x, the power rule is going to be n times x to the power n minus 1. So this expansion will give me a function that calculates the value of -1 over 1 plus x all squared. And that expansion, if I plug this in, I'm going to end up with 1, so -1, x to the 0 here when I plugged 1 in. I forgot need to, when I differentiate this, and there's a constant term in there that differentiates to 0. So I have one less term. So when I plug in that, I'm going to end up with -1. Plug in 1, I end up with -1. When I plug in 2 plus 2x minus 3x squared plus ... Okay, so that series represents the function -1 over 1 plus x all squared. Now that series also has a radius of convergence, and I can test this using a ratio test. So my ratio test is going to be the limit as n approaches infinity, the n plus 1 expression is going to be -1 to the n plus 1, n plus 1, x to the power n, and the n expression goes in the denominator, -1 to the n x to the n minus 1. And this needs to be less than 1. So I can group some of these terms together. So the limit as n approaches infinity, the -1, this part here just becomes -1. So I get -1 to the power 1. The n over n plus 1, if I group that together and do a limit, I'm going to end up with 1. So n plus 1 over n as the limit goes to infinity is just going to be equal to 1. When I simplify the x part, I've got an extra x in the denominator of the denominator, so that just becomes x in the numerator, and that's going to be less than 1. When I apply my limit, I'm going to end up with x. I'm just going to ignore the negative because it's an absolute value. This becomes, actually I'll write that in, so it becomes -1, which I don't have to worry about because of the absolute value. The limit of n over n plus 1 over n is 1, and then I have x to the power 1. So my radius of convergence is going to be 1. And I have from -1 to +1 as what I need to test. So then I test my endpoints. I'm going to test -1. And I plug that right into my original series here. So I'm going to do my series from n equals 1 to infinity, -1 to the n times n, -1 to the n minus 1. So what ends up happening is that if I put those -1s together, I get 2n minus 1, so that's always odd. So I end up with -n. So this diverges because it doesn't pass my my nth term test. My nth term is equal to infinity, so it's divergent. So I know that my endpoint here is open. So then I'm going to test my right-hand endpoint. So I'm going to test x equals +1. My series is going to look like this, from n equals 1 to infinity, -1 to the n times n, 1 to the n minus 1. Well, this is just going to be an alternating series of n, -1, n, the n. So this is going to diverge because the limit as n approaches infinity of our term, it does not exist. It's just going to flip between positive and negative, so it doesn't converge, so the limit doesn't exist for the nth term. So again, it doesn't pass this nth term test. Doesn't pass that. So there it is. My interval of convergence then works out to be, it's going to be open at -1 and also open at +1. This represents my interval of convergence.